Hi students, and the next topic today is Yagi-Uda antennas. The Yagi-Uda antenna is one of the application of wire antennas. It is the combination of many dipoles. Okay, so why the name is Yagi-Uda? The Yagi-Uda is the name of two scientists. One is Professor Shintaro Uda, is from Japan, and in the year 1928, and similarly the another scientist name is Hidetsugu Yagi. Okay, so these two scientists combinedly have made one applications that is called as Yagi-Uda antennas, right? So this is the structure of Yagi-Uda antennas, and it was developed in the year 1928 and commercialized by 1930. And what is the structure of Yagi-Uda antenna? See here, there are four major elements. The first element and longer element in Yagi-Uda antenna is called as reflector. The next to reflector, the element is called as folded dipole element. After folded dipole, there are elements are called directors. Here we have two directors. We can increase more than one directors, right? 1, 2, 3, 4 like that. And all the elements have been connected with a clamp that is supported. This is called a supporter. It is a horizontal support, and the clamp is made up of an insulator to avoid inductions, electromagnetic inductions. And among all the components in this antenna, only this folded dipole has been connected with a cable. Okay, and there is no physical connectivity between one another in this antenna structure. For example, there is no connection between reflector to folded dipole to one director another director like that. Then how it is possible? What is the purpose of these kind of antennas? The major three elements in this antenna is reflector, driven element, that is by folded dipole, and directors. Directors are also dipole elements, right? Okay. So all these are supported with the horizontal support, and the clamp is used to fix the antenna in the horizontal support. The clamp is made up of insulator, right? The coaxial cable has been connected with this driven element. This will act as a feeder line to the television. This is widely used for television antennas, right? And how to design a Yagi-Uda antenna? What should be the length we have to fix for a driven element, for a reflector, for the directors, right? So these are the formulas. So among these three, the reflector is high in dimensions, that is equal to 500 by frequency in megahertz, the unit is feet. For driven element, 475 by frequency in megahertz, the unit is feet. The directors, 455 by frequency in megahertz in terms of feet, right? So this is the design values of the elements which is used in Yagi-Uda antennas. The unit is in terms of feet. So while you are doing in the problem, you should understand the conversion of feet to meters, everything, and see the optimum value of the distance between the elements, that is spacing between the elements, and the thickness of elements, and the length of each element, right? FD is folded dipole, R is a reflector, D is the directors. Okay, right? So these are the spacing, right? So Yagi-Uda antenna is said to be a beam antenna. It is only 3 elements array, and more than 3 elements are there, right? If it is used for unidirectional antenna, and if you need to increase high directivity, more number of directors can be used. The gain offered by this antenna is 8 dB, and front to back ratio is 20 dB. That is very high. That is high front to back ratio says about high directional antennas. Right, I already told that in order to increase the directivity, more elements can be added in the array. Right, so another name of this Yagi-Uda antenna is called as super directive antennas, and it is a frequency sensitive, thus it is a fixed frequency device. It is used for a fixed frequency range. See this, there are two pictures it shows in this animations. The first is only with the two elements, okay, only with the two elements. What is happening, and here there are 3 elements, what is happening. In these 2 elements, this red color element is called as driven element, and this element is called as directors. Okay, only one director is there. And the second diagram, we have driven element, we have a director, we have a reflector. Okay, the reflector reflects whatever the signal is coming back. It is minimized. The reflector minimizes if there is any signal is coming in the backside. And towards directors, we have a maximum directivity. That is, the antenna concentrates maximum power towards the direction of the directors, right? So what are these two animation shows? See here, in the left side of the reflector, the electromagnetic induction has been generated with out of phase. See here, there are out of phase signals, or there is no in phase signals. So out of phase means the signal will be reduced. The current component gets cancelled. Towards directors, see here, the signal whatever is generated here, that is with respect to the space and length of element and the thickness of element. See how these signals are oriented. And towards these directions, all the signals are oriented. That is almost in same phase. So signal will be combined together. It will be added up. Okay. So towards directors, we are getting a high directivity because the signal which is produced from each element will be out in phase. And the backside of reflector, signal which is produced by each element is out of phase. So these are called as destructive rays, and these are called as constructive rays or constructive signals. And in this yagi wood antennas, and these are called as parasitic elements, right? Because first we are going to connect the feeder towards this driven element, and it starts radiating the signal, or it will act as a resonator, and so because of this resonance function, it will induce the electromagnetic field in the nearby conductors, right? So because of this mutual coupling, and this will be driven by this element, and even though there is no physical connection between these two elements, because of the mutual induction, the reflector starts generating the EMF, and similarly this will connect towards this, and this will induce EMF in the driven element, right? So because of these are called as parasitic elements. Parasitic elements are not interconnected together. Among the entire cases, only one element will be connected with the driven cable or feeder point, that will induce electromagnetic signal of all these nearby equipment. So these are coming under parasitic arrays. So it is the best example for parasitic arrays. So what are the advantages of yagi wood antennas? It offers very high gain, and high directional characteristics are there, and very good front to back ratio it produces. That is, it concentrates maximum power in the desired directions. It is a low cost antennas, and it is used for high frequency operations, and it is light in weight, and feeding mechanisms also very simple and power efficient. These are the benefits of yagi wood antennas. Thank you.